Okay, so good afternoon again. So today's focus, as I said yesterday, will be on the big data and especially focusing on how we can accelerate the different kinds of middlewares like Hadoop, Spark, and Memcached. And so as many of you must be knowing, I mean, this field is expanding. We have a lot of opportunities to process the big data and then make a lot of sense out of it. The rate of information growth appears to be exceeding like Moore's law, and those of you who are familiar, there is a lot of different V's are being introduced to characterize this kind of big data like volume, velocity, variety, value, etc. Now if you take a very broad look at the modern clusters or the data centers where this big data processing is taking place, you will see a picture like this. That means we have a front end tier where we have components like Memcached, the database like MySQL or HBase, and then in the back end we have the data analytics applications which are focusing more on the MapReduce, Spark, and HDFS, and these get done typically like offline, and these are online. So let's quickly go over some of these middleware, the architecture, just in case you are not very familiar with it. So the Hadoop has been there for many years, and broadly it was the Hadoop 1.x which was there, and 2 years back this Hadoop 2.x started. So the broad idea here is that in the Hadoop 1.x, both the cluster resource management and data processing, they were integrated together, and that was not very efficient. Now in the Hadoop 2.x, they have been decoupled, and we have a yarn component here which focuses on the cluster resource management and scheduling, whereas here MapReduce and the other models, they sit on top of that. And below each one of these components is the Hadoop distributed file system. So that is the one important component. We'll be taking a lot of look at that. And also there are other components like RPC. Then many years back, so a few years back, again a new paradigm has started called Spark. So that basically tries to provide in-memory data processing framework. So typically Hadoop is like a batch-oriented thing, so you just submit the job and get the results later. And the Spark is trying to focus more on the interactive data analytics. Okay, and especially here, like the target is to have iterative machine learning jobs. So that means if a job, you bring the data into the in-memory and continuously do processing over multiple iterations. And they have a new kind of design like a Scala-based implementation, and they have totally redesigned the infrastructure with some component like resilient distributed data sets like RDDs, which provides the performance as well as fault tolerance. And they perform also MapReduce like shuffle operations, and in the back end, the Spark still talks with HDFS. So the HDFS is still common between the Hadoop infrastructure as well as the Spark infrastructure. And the more we'll see, go inside, we'll see that all these middlewares have been designed with sockets. That's the traditional, the TCP/IP sockets that sits at the lower layer, and we'll see that that is the place where you actually don't get very good performance, and there are a lot of opportunities to accelerate. Okay, and we'll focus on that a little bit later. The third component which I'll be focusing is the Memcached, and this is actually used in a lot of data centers. In fact, a very common example I give, and in fact many of us actually interact with this kind of component. Let's say you are buying some airline tickets. All right, many of you must be buying from different airline portals, or let's say Expedia or Orbis or any one of these. Now, have you seen sometimes, let's say you do some search between, let's say, Zurich and New York, and you get very good price. Okay, then you click saying, oh, the price looks good, let me purchase. Then you get a very message saying that sorry, that fare is not available. Have you seen that kind of message? Okay, so it could be happening due to two reasons. The first reason is, of course, the ticket is sold out, that fare. But the other one is that most of the time the ticket is not sold out, but what was shown to you or what message you got is from the CAS. Okay, that means somebody else prior to you did the same search from between Zurich and New York, and whatever that price was being cast in that layer is being given to you. Okay, so the next time when you see that the price is not there, it actually that is the Memcached component, and it goes actually fetches the new fare and then gives it to you. Okay, so next time you see this, you could very quickly relate that, oh, I am interacting with Memcached. Okay, but now the question is, why do these data centers give you wrong information? They should not be doing that, am I right? Any clue why don't they give you the correct information all the time? Anybody has thoughts? Yes.
It's all about performance. When you have more requests than the server may deliver, you have to cache.
Yes. Now, I mean, that is one aspect. So they want to increase the throughput of the system, because a lot of queries are coming, and with a limited amount of resources, they want to give you the best, like the best results while trying to deliver the performance. But there is another aspect to it, why they do it. Anybody has a clue? It's just the performance or something else?
They just want an overview and then they go deeper.
Okay.
And if you do a cache base, that doesn't much of one.
Okay, so that is another reason. That means you don't have to be always the precise to get the correct result. And the other thing is that how many times do you search and how many times you buy? What is the ratio? Is it 1 to 1? 10 to 1? 100 to 1? 100 to 1. Bhushan is the real bargainer here. Okay. So 10 to 1 or 20 to 1, sometimes depending on like where you are flying kind of thing. So the thing is the number of reads versus the writes are very high. So that is the reason. And again, the users doesn't have to get the precise answer. They can click once more. Okay. So keeping all these type of considerations into account, you want to give good response time to the users. You don't have to be precise, and you know that the users have more number of reads. So that is the whole idea of trying to provide this kind of a Memcached, which is a distributed caching layer which allows to aggregate spare memory from multiple nodes. So if you have, like, let's say this is the Memcached servers, you take memory from each of the nodes. So let's say you just take like 16 servers are there, 2 gigabytes each, so you have 32 gigabytes. You can store a lot of data. Now, of course, that is only the memory, but you can also aggregate that with SSDs. Okay, and the SSDs are also fast. It gives you a big capacity, so you can combine the memory and the SSDs together also to design a much more bigger Memcached layer. And I'll try to show some numbers later on. And these are typically used to cache the database queries and the results of the API calls. So with that kind of a background, so the way I'll try to present here, first we'll try to see what are the challenges for accelerating the big data processing. I'll introduce our project, which we started like almost 3 years back. Yesterday I talked about the MapReduce project, which has been there for 15 years. So we wanted to take a lot of those experience and knowledge and then move it to the big data field. So this is a 3-year-old project, and since last year we started distributing software. So I'll talk about that, and then I'll try to show some case studies here. And the case studies, then I'll go into HDFS, MapReduce, Spark, etc. We just made a release like 2 days back. I'll try to show some performance numbers. And the other direction which is coming here also, traditionally this all, let's say Hadoop, people have been deploying separate clusters, saying this is a Hadoop cluster. But if you see, all over the world, there are also a lot of HPC clusters. So the question is, can they be combined? Okay. So let's say you have HPC cluster with Lustre, and you just want to run MapReduce jobs. So you don't need to go through the traditional HDFS. So the question is, can these two fields be merged, high performance computing and big data computing? And I'll try to show some results here. We have done like the HDFS with in-memory, Lustre integrated, so everything, you can run it on your existing cluster. You don't have to deploy a different Hadoop cluster. So I'll show you some numbers here. So then I'll also go into the Memcached and HBase. I'll try to show this, the hybrid design I indicated, like with SSD assisted hybrid memory. This release we did around 10 days back. Also I'll try to show RDMA based HBase. And while trying to do these designs, we have come across a lot of challenges in terms of designing a set of micro benchmarks. Okay, if some of you know, like in the MPI context, not only we have the MPI libraries, we also have a lot of OSU micro benchmarks we call. So over the years we have built those micro benchmarks. So similar kind of things we are trying to do it for the big data environment so that you can evaluate each one of these components in an independent manner. So as we know, like all the HPC cluster these days, if you see the high-end computing is growing dramatically. We have been hearing from a lot of talks. Broadly, you will see that these are the multi-core, many-core technologies. We have the RDMA-enabled networking, either InfiniBand or Rocky, and then of course the SSDs. And also now we are getting a lot of attention on this NVRAM, non-volatile random access memory, and of course the accelerators are there. Excuse me. So this is a chart, is a dense chart, but it shows actually all the different protocols which are available in the Open Fabrics consortium, those of you are familiar. So at the top level, you see like we have a application or middleware. Either it can go through the sockets. When I'm saying application or middleware like MPI is a middleware, HDFS is a middleware, or a Hadoop is a middleware. So they can either go through the sockets, and then you have all these choices, 1, 10, 40 gig, or even in the InfiniBand you have IP over IB, or the 10, 40 gig with Tor. On the right hand side, this is the native InfiniBand. Okay, and the focus here is that we don't go through the sockets, but we go through the verbs. That is the lowest layer in which we want to get the maximum performance out of the network, and this is where we go through the RDMA, the user space, so I call like a IB native. And the question is here is that, of course, to get all this performance, we have to move, let's say the middleware, as we saw examples like API or Lustre, all those file system or different components, they need to be redesigned with the verbs layer, then you can get the performance. Your end application need not be modified. If your middleware has been modified, then the end application just runs. So that is the kind of focus. So we'll try to see that how we can move, especially from the Hadoop and all, they are already running only on this mode, on the traditional sockets mode, though how we can take it to here. And as InfiniBand has been there for like almost 15 years, we know like MPI, all different MPI stacks are available, all these large scale systems are running MPI. Even the parallel file systems also, Lustre, GPFS, all of them have also moved. This is the kind of typical performance we see, less than 1 microsecond, around 100 gigabits per second bandwidth. And the third metric is also important, is the CPU utilization. So all these modern networking like InfiniBand, because it tries to offload a lot of things to the network, for the actual protocol processing, you will see that very little CPU is utilized. And that actually helps, because when you run the application on top of the protocols, then you get the overlap with computation and communication. Okay. So and that leads to very good performance and scalability. So like the picture I showed yesterday for like the MPI plus X paradigm, you can also think of like, let's say, what are the challenges in designing the communication and I/O libraries for big data systems. So here if you see like these are the applications, this is the big data middleware, HDFS, MapReduce, HBase, Spark, Memcached, etc. Currently they are only running on the sockets model. And below we have all these like networking technologies, the multi-core, many-core accelerators, the storage technologies. So this is where the different components of the communication and I/O library sit. Okay? And within that you can see like point-to-point communication or I/O file system, synchronization, threading model, QoS, virtualization, fault tolerance. So these are the components to bridge the gap, or either take the features from the lower layers and then try to give it to the upper layer. So when we started the project, the first objective we started is that instead of sockets, can we move it to RDMA? That was the primary focus, and I'll try to show you a lot of results on that. And then after that, we have started gradually taking a look at the upper level changes. The idea here is that all these stacks which were designed earlier had assumed slow network in mind. Okay. But now since we are converting them to RDMA and with all these features, so the network protocol aspects are becoming faster. So then the question is, can we revisit some of the upper level changes, and then if we can make those changes, we can put them together and get even more benefits. Okay, and we'll see some examples of that. So the broad idea, most of the results I'll try to show you. If you think of like the applications running with sockets or with 110 gig network, the sockets are not designed for high performance. There is some mismatch in the stream semantics. Zero copy is also not available for the non-blocking sockets. So we started asking the question that, can we have some new designs here, we call like OSU design, which can directly run over the verbs. And if we can do that, then it can actually run on InfiniBand or 1040 gig iWarp or any of the RDMA-enabled interconnect. It should be able to run. So so this is the project which we have been working. If you just go to the site, highbd.csc.ohiostate.edu is a high performance big data, that's what we call. So over the years, we have made actually different releases. We started with Hadoop 1.x, now we are into the mainstream Hadoop 2.x, we'll drop this 1.x support very soon. We also have the RDMA for Memcached, and also we have started introducing some of these HighBD benchmarks. I'll talk a little bit more about that. So currently it's around, the user base stands around 95 organizations in 18 countries. We have crossed around 2,900 downloads, and in the near future, I'll talk towards the end, we'll also have support for the HBase and Spark. I'll show some results for the Spark, but they have not been released yet. So this is the release which we made 2 days back. I'll go into a lot of details here. So the way this is like the Hadoop 2.x, it has actually has the RDMA designs for all the components like HDFS, MapReduce, RPC, everything together. Okay, it's not just only one component. And also it has also, this is also the HDFS with in-memory. Okay, so earlier HDFS has totally focused on only the SSDs or hard disks, so now we have a hybrid design. You can actually run HDFS with in-memory support. And also, you can run it with heterogeneous storage. So you can define it's a combination of in-memory, SSD, hard disk, or even Lustre. So you have a lot of flexibility depending on your system configuration. You can configure your HDFS to take advantage of the underlying things. We also introduced this, I was telling, MapReduce over Lustre. That means if you have an HPC cluster and you just want to run MapReduce job, okay, so you should be able to just use the existing HPC cluster with Lustre and then get the performance. You don't even need to install the HDFS at all. So these are all the new features which have been introduced. So I'll go into, it has a lot of different modes. I'll talk about this Triple H, we call it hybrid heterogeneous HDFS. So it has different modes. And what we have done is, so this is based on the latest Apache Hadoop 2.60 version. So that is the latest Apache Hadoop. What do you get? Yes. Sure.
For having MapReduce over Lustre, from a design point of view, Lustre works in a way that they have a client server where the logic of computing across all the compute nodes would be lost. Since I have this kind of communication with my data
Yes.
servers, so
Yes.
I don't have anymore this distributing computing on the client too.
So I'll show you. Yes, yes. So you can actually run the MapReduce from all the clients, and your data is actually sitting on the Lustre. Okay. We also have a mode. Either you can have the data on your local hard disk, or you can actually put it in the Lustre. I'll show you some concrete things. Okay. So what we do here is that it's to be noted that this is compliant with Apache Hadoop APIs. So we don't make any changes. So if you have some jobs which is running, let's say on the Apache Hadoop 2.60, this will just run directly. Okay, you just have to install our library and then it runs. And we also have easily reconfigurable modes for different protocols. So you can configure it to run on InfiniBand or Rocky or even IP over IP, which is the sockets. So whatever numbers I'll be showing, you should be also able to get all those numbers by just making those changes into the configuration. And similarly, like the Memcached, so we had the RDMA Memcached that was released a while back, and 10 years back, we actually introduced this new design, which I call like a SSD assisted hybrid memory. So that means not only you take memory from all the nodes, you can also combine with the SSDs or the different nodes, so that you can provide a very large amount of Memcached with a good trade-off in terms of performance and the capacity. So here again, we try to conform to the public version of the Memcached and the libmemcached. These are the sockets version, and we have taken that, and then we have enabled the RDMA version out of it. And again, you can configure between the different kinds of protocols. And then on the micro benchmark side, so we have only introduced the Memcached benchmarks that have become public, but we have a lot of benchmarks I'll talk later purely for evaluating HDFS, purely evaluating MapReduce or RPC. So they have not released yet. Gradually we'll be trying to release those things. So now let's take a look at some of the case studies and see what kind of performance benefits we see here. So what I'll try to do is I'll go component by component first, like just focusing, let's say, what we can do to accelerate HDFS alone. Then I'll say what you can do to accelerate MapReduce alone, and also the Spark. And then later on, I'll show you combined effect. Okay, so with respect to our releases, you can turn on all the modes. Everything is RDMA, so you should be able to see a combined benefit. So the way we approach this, this is like if you take a look at the internal protocol of the HDFS. So as many of you know, like this is the Hadoop distributed file system, which has like a replication. By default, you make 3 copies. You keep 1 copy, give it to your neighbor, give it to another to the rack. And that means this replication, which is the write, that takes the most of the time. Okay, so we wanted to accelerate that first, which is like a common case. So we wanted to accelerate that. So we enabled the RDMA based HDFS write and RDMA based replication. And typically what we do is the architecture looks like this. It goes through the Java sockets interface and then directly talks to the network. And so what we did is from this JNI layer, we had our design which directly talks to the verbs. Okay, so you can basically think that we are replacing the sockets and then directly going to the verbs for write operation. The read operations, we don't make any changes because it's a local read. And also there are a lot of control flows. We ignore some of those. They can still run over the sockets because those are not performance critical. So we have not done that. The other thing we have introduced is actually a parallel replication support. So this goes back to the architecture when I said like if the network becomes faster, you can think of some higher level changes. So traditionally, the Hadoop was designed with slow network, like the basic Ethernet in mind. So that's why when they do the replication, you first send a copy to somebody, he sends to somebody else, he sends to somebody else, and then you get the ACKs. So that is like a sequential replication, and it takes time. But if you have high bandwidth network, instead of doing sequential, you can just do write, and get the ACKs. So that's like a parallel replication. And that's what we have introduced also. You get more performance out of that. And then, of course, with any of these InfiniBand-based designs, you need to have like on-demand connection, some buffer management. Those are like the standard designs what comes with InfiniBand. So this was the first paper we presented at the SC 2012. That was the first design we put it there. Then last year we have enhanced this design to maximize overlapping in the RDMA enhanced HDFS. So this shows some number, the very initial set of number which was presented at the SC 2012. So if you just see the communication time, so that is like the replication time in the HDFS. The x-axis is different file sizes, like we are going from 2 gigabytes to 10 gigabytes. And what we are trying to show in the y-axis, there are 3 bars here. So in the same cluster, we have this, the blue one is the 10 gigi, and these 2 are running with InfiniBand. And in this case, it was InfiniBand QDR. And the 2 protocols, this is the IP over IP, that is the standard HDFS without any changes. It can run with IP over IP. And this is our new design, the RDMA design. Okay, so we are comparing on the same cluster 2 different networking technologies, and with InfiniBand again 2 different protocols. Okay, so here effectively, if you'll see, just only taking the InfiniBand by changing from sockets to RDMA based design, you can see almost you will get 30% improvement. The same network, the same hardware, but if you just change the designs from the sockets based to the RDMA based, you get around 30% improvement. And the comparison with 10 gigi, that is like a reference point here, which gives around like 56% improvement. Most of the later numbers will actually compare between IP over IP, which is the sockets version, and the RDMA version. So this is the new design which will be presented in the CC Grid conference in 2 months. So this is where we brought this HDFS with in-memory as well as heterogeneous storage. So what does that mean? So that means you can actually configure your HDFS to run with RAM disk or with SSDs, hard disk, Lustre, or in a flexible manner. Okay, and it has different kinds of properties. I'll try to show you in the next slide. So it has 3 modes. One is the default mode, one is the in-memory mode. So that means completely you can run it from RAM disk. Okay, and that will give you the maximum performance. Or you can also do Lustre integrated, we call it like HHHL. This is the in-memory, which is the memory M. And there are different kinds of policies to utilize these storage devices. You can say it's a combination. I want a RAM plus SSD, or you want a RAM, SSD, hard disk. So all these combinations we provide. And then there are different kinds of eviction promotion schemes. There are hybrid replication, and also we have Lustre integrated mode, where we want to, in fact, take advantage of the Lustre, because Lustre has already fault tolerance. And so that when we are trying to do the HDFS, we don't need to make 3 copies. We can keep only 1 copy in the Lustre, and Lustre is fault tolerant, so we can leverage that to give performance. So here, these are the 3 modes. So broadly, it is the default mode in our release. If you just download and run, that is like the default mode. But we also allow these other modes to be configured with some parameters. So this is the I/O operation. It can have over RAM disk, SSD, and HDD. And this does a hybrid replication. So that means you keep some data in memory, like 1 copy, and another copy you can keep it in the SSD, which is like a persistent storage. And this has like a better fault tolerance as well as performance. And then the HHHM, which is a purely you do the memory replication in memory with lazy persistence on the SSD. And here you will see that you get tremendous benefit because it is coming from the memory oriented operations you get. And then this is the mode which is Lustre integrated. So that means if you have an HPC cluster with already Lustre, you can take advantage of that. We can try to leverage the Lustre based fault tolerance, so you don't need even HDFS replication, and also you can have reduced local storage space. Okay. So let's take a look at some of the numbers. So this is the default mode. This number has been taken on the TAC Stampede. I introduced that system yesterday. That's the largest InfiniBand cluster at the Texas Advanced Computing Center. So if you take a look at, this is the InfiniBand FDR. So what we are trying to show, this is a benchmark which is commonly used to test DFS IO. For evaluating the HDFS performance, that is a standard benchmark. And in this case, here we see for a 160 gigabytes of test DFS IO in 32 nodes, we can improve the write throughput by a factor of 7. Okay, so it's not a few percentage; it is by a factor of 7 we are able to push compared to the IP over IP. Similarly, the read throughput we are also able to improve by a factor of 2. And then here is another benchmark which is like random writer, which with the different kinds of ratios. Here in the 32 nodes, we try to like this is the 8 nodes, 30 gigabytes, 16 node, 60 gigabytes, 32 node, 120 gigabytes. So again, here we can see like the execution time improves by a factor of 3. Okay. Then this is the another set of numbers taken from the SDSC, that's the San Diego Supercomputer Center. They had a supercomputer called Gordon, and in fact that every node on that cluster has SSD. Okay, so we have run these experiments here, and what is trying to show in this one, the standard is the sort, that is a standard benchmark in the Hadoop domain. So here we are saying like the different data sizes, 20 gigabyte or 40 gigabyte or 60 gigabyte. So here we are trying to show how the execution time changes. Like this is the standard HDFS over IP over IP. This is the Lustre over IP over IP, and this is the new RDMA design. So here you can see again, like we get around like 54% improvement compared to the Lustre. But the more important thing here, if you see, let's say you have 60 gigabytes, so that means 60 gigabyte in, 60 gigabyte out. So it's 120 gigabytes. That is the data size. So if you go through the standard HDFS, you will require like 3 copies. So your amount of storage is like 360. If you go through the Lustre, because Lustre is fault tolerant, you just is good enough just to keep only 1 copy. If there is a failure, you can recover from the Lustre. So you just need only 1 copy, 120. And in our RDMA design, we actually keep like 1 in the in-memory, and then another one is the SSD. So we also have somewhere intermediate storage requirement, and we can give you the best performance. So then this is another evaluation. Like there is a PUMA workload. It's from Purdue. If some of you are familiar with like the scientific MPI, there is a NAS parallel benchmark. People use it to evaluate different kinds of workloads. So similarly, Purdue has introduced something called a PUMA with different kinds of kernels which are used in the big data area. So here like there is one is called sequence count and the grep, And here we see like in that HHL, the Lustre mode, we get around like 17% benefits over Lustre, and the grape we get around 29.5% benefit. There is also another application here. We have taken the Cloudburst, which is like a bioinformatics application. People use. So there again, you will see that compared to the IP over IB, the HDFS, here we can give you almost like 19% benefit with the new RDMA design. So these are some sample numbers. If you go to our website, in fact, we have put together a lot of numbers there. So I'm just, because of the time, I'm just trying to show some highlights here, but please feel free to go to the site. You will see a lot of different kinds of numbers. So now let's move to the MapReduce side. So if you just take even the MapReduce itself, what we did is we actually introduced the RDMA based shuffle. So here if you see, like instead of Java sockets, again we take the JNI and then put our OSU design with the verbs. Here we have in fact a lot of in-memory merge, and we also do a lot of over the years we have introduced different kinds of overlapping techniques to provide overlap between map, shuffle, and merge phase, as well as shuffle, merge, and reduce phase. So in fact, the next slide shows that. So if you see the traditional MapReduce, this is how it happens, like map, then shuffle and merge, and then only reduce starts. Okay. Now in our in-memory merge, like last year we introduced this scheme so that you can have map and shuffle and merge starts here and then the reduce. So you get like better overlap. And finally, the last year we presented this paper at ICS, where in fact we tried to exploit in fact much more overlapping. So map, shuffle, merge, and then the reduce starts as soon as the map gets done, so that all the 4 phases are going concurrently, and then you can get the maximum benefit here. So here it is some sample numbers here. We are trying to show sort and terasort. These are the common benchmarks which get used. And these numbers have been taken, like this is a OSU cluster and this is on the tag Stampede. And for different data size and cluster size, we are showing 3 numbers here. All are running over InfiniBand. And so the orange one is IP over IB. And then the green one is actually from Mellanox. They have the UDA accelerator, unstructured data accelerator. So we are comparing that with our RDMA based design. So broadly here you will see that we are almost giving, like compared to the IP over IB, we have almost like 40% benefit giving compared to the sockets based design. And here on the tag Stampede, we get similar kind of things. If you go to like 64 nodes, that is equivalent to like 1,000 cores. So we are running MapReduce over 1,000 cores, and for a 320 gigabytes of terasort, we can give you around 38% benefit for over the IP over IP design. So then this is the PUMA workload I was telling, like the Purdue workload, like the NAS parallel benchmark. So they have many of these smaller kernels which are being used in the big data area, like let's say adjacency list, self join, sequence count, word count, invert index. So just like the NAS parallel benchmark, these benchmarks demonstrate different kinds of computation and communication characteristics. Okay, and of course, if some benchmark is communication oriented, then only we'll see the benefit. If it is a compute oriented, because that's what we are trying to accelerate. Okay, so what we are seeing here, like for example, let's say word count, which is compute intensive, you don't see much difference between these different designs. Whereas, let's say sequence count or self join, here you will see that like you get self join, you see around 50% improvement for 80 gigabyte data size, and then here you see around 49% improvement for 30 gigabytes. So now let's come to the Lustre. So this is where Hushan you were asking. So the idea here is that let's say you have an HPC cluster and you just want to run MapReduce. That's all. Okay. So the way you can think of, let's say single node, you can have like the Lustre client running here, and these are of course the standard metadata servers, object storage server, Lustre setup. So we can actually have on the clients, we have the mapper running as well as the reducer running. So broadly, you will see that there is two different choices here. For example, let's say you might have this HPC cluster with local disk or without any local disk. So you see 2 different kinds of deployment. Sometimes you have local disk, sometimes you don't have. You just focus on the Lustre. So we have provided both the solution. You can configure local disk to be used as the intermediate data directory, or Lustre can be used as the intermediate data directory. So what we have done this design, This is like we'll be presenting at the IPDPS conference in 2 months. So you can think like, let's say the multiple mappers, this is your intermediate data directory. So now there are choices. Either you can do like from the RDMA based design of the Lustre. So you are accessing the Lustre, but now instead of the sockets based things, you are going over RDMA. And you can have Lustre read based shuffle or RDMA based shuffle. We also have some hybrid shuffle algorithms, and it dynamically adapts, and that also works together with the in-memory merge and the overlapping I indicated earlier. So here are some sample numbers we presented at the Europar last year. So here if you see, it's a local disk is used as the intermediate data directory. Okay, and this is again taken on the tag Stampede on 64 nodes, almost half terabytes of data. You are trying to do the MapReduce, you will see around like 44% improvement. Okay, once again, it is the same hardware. We are not making any changes. Again, the existing HPC cluster, but we are providing a framework which is the RDMA based design to speed up your sort application. And here also similar kind of things. We see it on the for 640 gigabytes of sort in 128 nodes, we get around 48% improvement. So this is with the local disk. Now, if you don't have local disk, so you can always go to the Lustre. Okay, so that means as the mappers are generating the data, they are putting into the Lustre, and then the reducers are also reading from there. Okay, so here you will see that here what we are trying to show, this is like IP over IB. This is the OSU Lustre read, this is the RDMA design, and this is our hybrid design. That is the best combination. So here you will see that on 8 nodes, we get around 34% improvement. For 128 gigabytes of terasort, we see around 25% improvement. So these improvements are a little bit lower than the previous one because, once again, Lustre is a shared file system. So all these mappers and reducers are going, so there is more contention. So you still get the benefit, but it's not as good as if you have a local disk. Then you don't see a lot of contention, and you get higher benefits.
So is that applies also in scaling? So if we go for more and more nodes, do you believe that still this ratio will continue, or it will drop?
At some time it will saturate, because it depends how you have configured the Lustre file system. If maximum you can handle so many clients, beyond that you will not go. Okay. Yes.
For example, how much occupied?
Pardon me?
How much was the Lustre file system occupied?
How much Lustre file system? So these experiments we are just running on the standard production stack Stampede. So I mean it's a production cluster. So we don't have any control how much was used. Okay. Any other quick questions? Yes. Regular local drives, yeah. There is no specialized things. Okay. So let me move ahead with the Spark. So as I introduced, the Spark is the newer architecture which is coming up. So we have just done some initial investigation. We had a paper at the Hot Data Connect last year, so we have not made a release out yet, but in 3 to 5 months you will see a new release coming out on this. So here the idea is that if you take a look at the internal Spark architecture, you will see like, again, they have like Java and IO shuffle server, native shuffle server. So what we have introduced is RDMA shuffle server. Okay, and this is a plugin design, and also we've introduced the RDMA shuffle feature, and that both these things work together, which can go through the RDMA based shuffle engine, and then that can run over the InfiniBand or any of the iWarp based systems. So here these are some initial numbers. So there is one benchmark which is commonly used in the Spark. It's called GroupBy, and here again what we are trying to show, this is a smaller scale experiment we presented in the paper, like only 4 nodes or 8 nodes. So you can think of like 64 cores. So here compared to, like we see compared to IP over IB, we get around like 18% improvements, and on the 8 hard disk node we get around 20% improvement. So our plan is to actually to give the best benefit to the Hadoop, because that has been there for some time. Things are much more matured. Spark is good, very rapidly changing. So once we stabilize the design in the Hadoop and we understand all the interplay, then we are going to move to the Spark, and then this is where we'll try to introduce the RDMA based designs. So now let me show some sample numbers. These are individual numbers I showed, but now if you just download our release, that has all the, like the HDFS is enabled with all these RDMA based things, the Lustre integrated in memory, all those features. MapReduce also has RDMA. Even I didn't talk about RPC. That also we have enabled RDMA. That's the RPC calls in the Hadoop stack. So this release, this like a, if you take the complete release and then run it on the default, which is the HHH mode. So this we are trying to show again on the test DFS IO on the tag stampede. So here you will see like 80 gigabytes, 100 gigabytes, or 120 gigabytes. For 80 gigabytes, you can improve the performance almost 6 to 8x. Okay, not just percentage. You are getting the maximum benefit here over 32 nodes with 128 maps, and similar kind of the latency reduction we can give you here like a factor of 2.5 to 5 to 3. This is the random writer and TerraZen. Again, those are like the standard benchmarks people use. Similar kind of things here we see on 32 nodes. That is like 512 cores with 128 maps for 80 to 128 gigabytes of file size. You can see an improvement by almost factor of 3. And here you can see the TerraZen. You can see a factor of 4 to 5. Then this is the other mode, the HHH mode. Similar kind of things here. We are giving all these details, how things were configured compared to the IP over IP, the RDMA based design. We get around 40 to 52% improvement. This is TerraSort, similar kind of things we see here. So then this is the HHM mode, that is the in-memory mode I introduced. So you can configure it to totally run it from the in-memory. And this is on the tag stampede and the SDC Gordon. Again, in the in-memory, you'll see like, because RDMA and in-memory, they work very nicely together. And if you combine it, see a factor of 28 benefits. Okay, so you will see like a 60 to 100 gigabytes file size, you get a 28x improvement by moving the HDFS to the in-memory. And then with SDC Gordon, here you get around like a 6x improvement. So these are some more test DFS IO and the sort, again on the SDC Gordon system. This is the HHL, that means the Lustre integrated mode is running here. So what we are seeing is the test DFS IO, the write throughput we are improving by a factor of 9. Read also we are trying to improve by a factor of, like not factor, it's like 29%. Okay, because it's a Lustre, so we are trying to read from the Lustre, and we use the RDMA features there to get the benefit. And if you run here like the sort, around 28% or 50% benefit you see. So once again, these are the sample numbers I showed. Please visit the website, and this is a complete release. So if you want to run it, just download, and you should be able to exactly get similar kind of performance benefits. Any quick questions here?
I will let you know.
Okay, sure. Okay. So let me then move into the Memcached and HBase. Here again, I indicated the Memcached I had introduced earlier. So now the choice in the Memcached is that whether there is a Memcached server and the client. So now the question is the client enabled of RDMA? If the client is not enabled with RDMA, then you cannot really take advantage of it. So what we have done is a hybrid design. So that means in the original it was like sockets worker thread. We have introduced some verbs worker thread. And so if the client is RDMA enabled, we attach it with the verbs worker thread. Okay, so that it can operate on the RDMA. Otherwise, it remains with the sockets worker thread. And this is the number taken on the tag stampede with InfiniBand FDR. So here you will see that compared to IP over IP, like a Memcached gate latency. So let's say 4 bytes or 2 kilobytes, the latency is reduced by a factor of 20. Okay, instead of like the Memcached operation happening over sockets, if it goes through the instead of IP over IP with the RDMA, you can get factor of 20. Then we did some scaling experiments. So this was like 4,000 clients. So we took 4,000 clients and did a huge Memcached aggregation. Okay, and in that case, we tried to, like, for very short messages like 4 bytes throughput. If you see here, the aggregated throughput, we are able to push it by a factor of 2. Again, with a very large Memcached, we are able to push the performance. Then we did also some evaluations with the different kinds of like the online data processing workloads. So here it shows like the Memcached IP over IP versus RDMA. This is like a read cache, read access pattern using the MySQL slab. So that is a standard benchmark which is used in the Memcached domain. So here we can see that it's reduced by 66%, or the throughput is pushed by 69%. So in fact, next week we are presenting this paper at the ISPAS conference. So then recently, as I told, like we have the latest release has hybrid support. So that means you can not only take the in-memory but also the SSD. So you can combine, let's say every node has memory, you take some part of the memory and some part of the SSD and aggregate them together to get a big capacity. So what we are trying to show here, this is like some standard benchmarks for mem latency and mem throughput. So what we are trying to show here, this is like the IP over IP, and then these two designs, this is a pure memory design, and then this is the hybrid design. Now obviously the pure memory design, you have only limited space. So depending on your capacity, how much you can cache is limited. But if you go to the SSDs, then you can expand that. But of course there is some penalty, like how the data gets evicted, how the data gets moved. There are some underlying protocols taking place. But what this is trying to show is that both these are performing very similar in terms of performance. That means we are not degrading any performance here, and at the same time we are trying to provide the throughput, we are improving by a factor of 2. And this diagram also is trying to show similar kind of things like the success rate. So that means if you have like your workload and if you cannot fit it in the in-memory, then you will see like there will be failures. Okay? But on the other hand, if you increase the capacity by taking the SSDs, you should be able to run that workload with 100% success rate. That's what it shows. And here we are trying to, while maintaining that success rate, we are also trying to reduce the performance, not reduce like gain in the performance by 53%. So this is a very practical design. So if you are trying to build any Memcached server, please feel free to download this, and you should be able to take both advantage of the in-memory as well as the hybrid. So we have done also some HBase, which is the other database component here. Similar kind of designs we have done. This has not been pushed yet into the release. We plan to do that. Here is just some sample numbers. Like again, like this is the HBase gate latency, and then here is the put latency. This is like the IP over IP. This is the RDMA, and this is the 10 gig. So we see around like again a 40%, 42% improvement with the RDMA design. So with that kind of a background, like what we have touched so far in this bigger picture, like we have done some point-to-point communication, some threading models and synchronization and I/O file systems. We have moved to the RDMA and have done some upper level changes, but not completely. That is still ongoing, and just to explore what additional things we can do at the upper level so that we get the best benefit. But more importantly, while trying to do these designs, we found out that there are all these benchmarks like SORT, TerraSort and all, which are really higher level benchmarks. Okay? So what we found out that the current benchmarks provide some performance behavior, but for a developer or a designer, they don't give you a lot of insights. Okay? Like for example, what is happening at the lower layer, where the benefits are coming from, which design is leading to benefits, which component in the design needs to be changed, or can performance gain or loss be correlated to the performance gain or loss observed at the upper layer. Okay? So I can give an example. It is like designing a car. Okay? So think of like a car. You can use a metric called mileage per gallon. Okay? That is a very high level metric. So think of the design team which is trying to design the engine, or the team which is designing the tire or the transmission. They need different kind of benchmark, okay, just to see to do the tire design in the best possible manner, or the transmission. Then they can be put together, and if the car runs, then you can measure the mileage per gallon. Okay? So that is the kind of problem what we saw, and this is nothing new for us. In fact, in our MPI project, when we started it like 15 years back, we exactly saw the similar things. So that was our motivation of introducing this OECU MPI micro benchmark suite, so that every time we add some new features over the last 15 years, this has become a pure industry standard now. So we introduce, every time we push a feature to our library, we also push a benchmark, so that you can actually compare and then see the benefits. In fact, this has become a lot of, like recently if you see a lot of procurement of large systems, you see a line saying report performance numbers with OSU micro benchmark. So that's what we actually want to do in the big data. So if you see these current benchmarks at the lower layer, there are no benchmarks, and on top of it, there are no correlation. Okay, and what we want to breach this cycle. That means we introduce the micro benchmarks here, and we also make sense out of it, like which component is helping or what design is helping at the upper layer, so that it will lead to more accelerated way of designing these next generation systems. So to do that, we have actually done, these are all published numbers, published papers, but they have not been pushed. For example, HDFS. If you just want to isolatedly study HDFS, okay, so we have a benchmark which can measure like sequential write latency, random read latency. You can actually change different file size, HDFS parameter, number of readers, writers, etc. This we presented at the WBDB 12 conference. Similarly, we have the RPC, just to measure the performance of the RPC, the remote procedure call. We have a latency test, throughput test. You can configure all these different parameters and then see how your RPC design is comparing against somebody else or how to optimize. And similarly, pure MapReduce. If you think of, like I showed earlier, the DFS-IO, but the DFS-IO benchmark brings also HDFS. To evaluate MapReduce, you are bringing the HDFS component. But the question is, can you evaluate MapReduce alone without any other components? So we have introduced this benchmark. We introduced at the BPOE conference last year. So here it can actually 3 different micro benchmarks based on the intermediate shuffle data patterns. You can have intermediate data is evenly distributed, or data is pseudo randomly distributed, or unevenly distributed. So you can actually configure these and then try to see how your MapReduce component itself is performing. So that is our plan kind of things moving forward. As I said, like the Spark design we are working on, and also the HBase. And the more importantly, this is what you will see very new future. We are getting a lot of requests to have these designs available as plugins. So currently it is an integrated design. That means, let's say Hadoop 2.6, you take our version, any application which runs with 2.6 can run here. But the question is, can it be integrated with, let's say, Cloudera, or can it be integrated with Hortonworks? So as of this, no. But we have designs being worked out, so that we want to convert our design into like an RDMA plugin. Okay, so that if you have a Cloudera distribution, you should be able to just use all our features, or Hortonworks or any other enterprise distribution, you should be able to plug in and proceed. So that is our next plan. And then, of course, all the micro benchmarks I indicated earlier, those are the things which will be released. And also, we have been actively taking research aspect of different kinds of threading model, virtualization, the accelerators, how do you take GPUs, how do you take the Intel mic to accelerate the big data applications together with our stack. And then advanced designs with upper level changes and optimizations. So to conclude here, what I presented like an overview of the big data processing middleware, discussed the challenges in accelerating the middleware. I presented some initial designs and also presented challenges in designing the benchmarks. Results are promising, but of course this is still an evolving field. So there are a lot of other open research issues are there, and then as a community, we need to actually come up with good solutions so that we can put together this kind of a high performance big data computing in the near years. So just like yesterday, I want to thank to all my past and present students, staff members, those who have contributed here. These are the standard pointers. I also want to point this out. In fact, as these two fields are coming together, high performance computing and big data computing, so we have actually put together a workshop. This is at the ICDCS, International Conference on Distributed Computing Systems, will be held in Columbus in June. We had a call for paper. The papers are going under the review. We have very nice 2 keynote talks, and there will be a panel. So please feel free to take a look at this. If you are interested, please visit Columbus, Ohio. I'll be happy to welcome all of you there. And last but not the least, I always show this. I am always continuously in need of good people. If you are a PhD student, postdoc, scientist, programmers, if you want to come and help us with some of these big important projects, you are always welcome. Okay, so with this, let me stop here, and if there are any quick questions, I'll be happy to answer these. Otherwise, we can talk offline. Thank you.